Okay, welcome back, everybody. And thanks to everybody for all the kind words. And it's good to be back in person. It's actually much better than being online. I guess after having 2 years with COVID, it's not the best solution to actually be online. So hopefully, if nothing happens, we're going to be here for the rest of the semester. And this week, we're going to have a standard lecture today, because we have to go through some formalities. And then we are going to, on Wednesday, we are going to have a kind of mix of exercises and, again, more formal stuff. And then Friday, we are going to look at the solution of the exercises, as we've been doing before. And we have, obviously, office hours after these lectures. And if you feel tempted, on Tuesdays in the evenings from 8 to 9, we have additional office hours if you want to join and keep me in company in the evening. So the exercises also this week, if you looked into the homework number 4, it's actually a continuation of homework number 3, the numerical part. But now, instead of just looking at this object which falls and hits the ground, you're going to add a model for the normal force and just see this object bouncing up and down till it comes to rest. So the only thing you would need to do with respect to the previous exercise you did is to add a normal force. And that acts, obviously, when the object hits the ground. And we have to model that one, because that's not a fundamental force. So one of the things which I want to do today is repeat a little bit of what we did last week. And then there is also a set of exercises we're going to look at in class on Wednesday. They are not that difficult, but it's actually okay to run through them. So we're going to use something like 10-15 minutes on that. And you can see these exercises. So we are going to look at whether these are conservative forces or not, which means that we need to calculate the curl of the forces. And if that one is 0, then this is a so-called conservative force. I'm going to repeat the definitions of these kind of forces today. And many of the fundamental laws of nature, they behave like this. The first one, which has essentially just a component in the x direction, there we don't need to do any calculation at all, because the curl is automatically equal to 0 if you're just in one dimension. So remember that the curl is a cross product, right? So that means that the vector which you produce by the cross product stands perpendicular to a plane. Now, the next thing which I wanted to emphasize a little bit is there's a figure here which Julie made, and she was a former TA here. You're just fantastic, by the way. So let me try to reduce the size here so you can see it properly. So this figure here actually contains, so this is a so-called one figure to rule all forces. So this figure here links many of the basic concepts which we are going to use in this course here. So you will see typically, if you have the acceleration, if you look at the highlighted writing of acceleration, you can calculate the velocity and position by integrating, but you can also get the acceleration from the force. If you have a potential energy, you can get the force, and vice versa, you get the momentum. You can calculate angular momentum and the torque, which is just the time derivative of angular momentum. And then if you look at this, you will see other examples. There are definitions of things like the gradient, if you have forgotten about that, because we are going to use the gradient quite a lot. And then you see some of these other vector relations which you have seen before in the different homeworks. So take a look at this one. This is a typical figure which you print out, and then you place it on your bedpost and you look at it before you go to sleep. It's a guarantee you're going to have beautiful sleep. Guarantee. When you look at this one, you're going to fall asleep immediately. But this contains, in a very nice way, many of the things which we actually end up doing here. So feel free to use it. I think it's a very pedagogical one and pretty useful. So let's go on a little bit And I wanted to repeat some of the things here before we switch to the whiteboard. So conservative force is a property whose a force whose property is that the total work done on moving an object between 2 points is independent of the path. And some of you may have seen this proof in mathematics courses. So when you started to look at multivariable analysis and you were introduced to partial derivatives and things like a line integral, have you seen this concepts before? And there probably you've seen the proof of the relation between the path independence and the fact that the curl has to be equal to 0. So in the slides for this week, at the very end, you will see a repetition of some of these things which you may have seen in mathematics courses. So we are going to use the results. But if you wish to refresh what you saw in mathematics, you can actually go to the bottom of the slides and you will see the same argument again. So I won't repeat this in the lectures, but I've included them for the sake of completeness. So there are two important conditions. And these important conditions are conditions which we are going to play around with. And one of these is that the curl is equal to 0 and that the force depends only on the spatial degrees of freedom. So the spatial degrees of freedom is a so-called necessary condition, and the curl being equal to 0 is actually the important condition. So these two conditions are those which give us a force which, when it acts on a segment or on a path which you're taking, the final result, the difference between the initial velocity squared, the kinetic energy in the beginning and at the end, is going to be independent of the path which we take. And that's a very powerful mathematical statement. So and then things which we looked at last time was, and I'm going to repeat some of these things now when we begin on the whiteboard here. I just wanted to quickly remind you of some of these things. So the total force is actually, if we now have two objects, 1 and 2 here, that's given by the derivative of the momentum, the linear momentum of the first object and the second object. And this is now summarized in this uppercase variable P. And the force is a sum of external forces plus internal forces. And if we have internal forces only, then we know from Newton's third law that F12 is equal to minus F21. So these two internal forces, they cancel each other. And then we're only left with external forces. So if we have a system, like when we are going to study the solar system, we are going to look at that as an isolated system. And then the sum of all the forces, of the internal forces, has to be equal to 0. But there is obviously a force which acts on the Earth, from the Sun, from Jupiter, from Mars, and so on. And that determines the motion of the Earth and the other planets. But if we don't have any external forces, then linear momentum, the time derivative, is equal to 0. And then we say that the linear momentum is a constant of the motion. And last week, we actually showed that this applies to internal forces for many objects. We looked at it for 1, 2, and 3 objects, and then we went to many. And then we showed that due to Newton's third law, then if we only have internal forces of the two-body character, they cancel each other. And then we have an internal force, a net internal force, which is equal to 0. And then linear momentum is conserved. And then we also looked at angular momentum, but let's move over to the whiteboard so that I'm not going to bore you all with just slides here. Any questions so far? Things which are unclear? By the way, I will keep with the Zoom connections in case you don't have the possibility to be here, in case something happens or your dog runs away. You may ask why I always bring up my dog, because my dog always did that. Especially in critical moments when you have to go to work at a special time, she always disappeared. Anyway, something may happen. So we will always keep the Zoom sessions going, and the lectures will be recorded throughout the semester. So you can always rewatch the lectures in case you missed something. Okay, so let's switch to the whiteboard and go through some of the material which we promised to look at today. So let me just switch here. Okay. So what we saw last week when we defined the net forces, net force, that was equal to the external force plus the internal forces. And if we only had internal forces, they would cancel each other and the total net force would be equal to 0. So the thing which we saw then is that when we summed over all the objects which we had, and we looked at the internal forces, so that would be the definition of the total internal force. That is something which, if we have a two-body interaction only, or two-body forces, then this was given by a sum over I, so it's a double sum, I different from j up to n, and then we would sum over Fij. And what we showed last time is this is equal to 0 due to Newton's third law. And then if no external forces, F external, what that meant was that linear momentum, since the force which we have, internal force plus the external forces, that is the same as the time derivative of the total linear momentum. And we have assumed that the masses are time independent. That's an important assumption we made here. And if that one is 0, because we have no external forces, then what we would say is linear momentum is a constant of the motion. There is an interesting side effect here, or an interesting addendum to this, and that deals with the center of mass position. And you may have seen the definition of that before. So we are going to use an uppercase letter R to indicate the center of mass, and that is weighted by the masses of all the objects which we have. So this is Mi, and multiplied by their positions, and it's divided by the total mass here. So the masses are additive, and we would typically rewrite this as a sum over all the momenta which we have, because this quantity which you see here, I equal 1 up to n, this quantity here, when we take the derivative, is now going to be equal to the momentum, but let's keep it like this for now. So this is equal to m. So if I take the derivative with respect to time, and we assume that the masses are constant, so they don't change as a function of time, then this is nothing but the derivative of I equal to 1 up to n, and then we would have mi of dri of dt divided by the total mass. And we know that this quantity which we have here, this one is nothing but the velocity times the mass, and so this is the total linear, the linear momentum for this specific object I. So this is the same as the linear momentum. And when we sum over all the linear momenta, this becomes simply the total linear momentum divided by mass, which is the same as I equal to 1 up to n of P of I divided by the mass, total mass here. And then clearly, if this dP dt is 0, that means that P is a constant, which again, since P is a derivative of R divided by dt, that means that d of R dt is also a constant. So that means that the center of mass, R, if we have a case where the total momentum is time independent, that means that R moves with constant velocity. And that's an interesting statement. So if you think of the solar system, this is actually perhaps one of the closest things we can imagine. If you look at the solar system and we calculate the center of mass of the solar system, so these M's which you see, they would be the masses of the different planets, the moons and the sun. That means that if total linear momentum is conserved, then the total solar system, its mass center, moves with a constant velocity. And that's an interesting statement for astrophysical and astronomical interpretations. And I guess that there are pretty many of you who are going to do a major in astronomy, right? So how many of you are doing a major in astronomy? Yeah, you probably encountered some of these arguments already. So mechanics and astronomy, they are like topics which are intimately linked with each other. And much of the mechanical laws which we have, they actually derive from astronomical observations, which humans have been doing for millennia. So there's a lot of history of science connected with astronomical observations. So this is something we will come back to a little bit later. But this was a small digression. Now, the other thing which we looked at last time was the torque and the angular momentum. So let me just repeat quickly one of these. And we are going to link this discussion with one of the exercises for this homework. So I wanted to show you how you can get started with one of the exercises here. So if you look at the torque and the angular momentum, so let's just write that one down. So the angular momentum, if we now think of a coordinate system with X, Y, and Z as we did last time. So I'm repeating a little bit of the things which we did last time. So X, Y, and Z. Then we could now think of momentum and the position spanning out a vector in the plane here. So we could now think of this being P, which is M times V. And suppose now that they live in the XY plane, that means that if I take the cross product, L, which is the angular momentum, that's the cross product of R times M times V, which is actually R times P here. So that means that for this specific case, if X and Y define the plane which is spanned by momentum and position, it means that our angular momentum is a vector which moves in the Z direction. Because that's orthogonal, since this is a cross product, that is a vector, resulting vector, which is orthogonal to the plane which is spanned by the two other vectors. So the what we saw last time is that when we calculated the derivative, sorry, this is a little lowercase l of dt, so the angular momentum, what we found last time is that this is now given by the following expression. So we found that this is given by r times the derivative of the momentum with respect to time, and that's the same as force, no, position times force here. Now, this is a relation where we can actually use exercise 4 from the first homework. So this is one of these vector relations which are useful to remember. And what we found as well is that the quantity of dl dt, which is now the sum for the individual objects of I equal 1 up to n, and then we have d dt of L of I. These are the individual angular momenta if we have n objects. So this should be an uppercase N. If we then have a conservative force, and this is what we showed last time, if a conservative and internal forces only, then we found that this quantity dl of dt, which defines the torque, which is how much angular momentum changes as a function of time, was then equal to 0. So this is also one of the things which we showed last time. So if you go back, I just wanted to repeat some of the key points from last time. And now one of the things which I wanted to look at is a calculation of the torque, tau, for a single particle or single object. And this is related to the next homework, and it's exercise 4 here. So I just wanted to show you one of the typical paths which we can take when we now want to calculate different quantities. And clearly the torque is an interesting quantity because that tells us how fast an object is rotating. So remember now that if you have momentum and position which spans the plane and you have angular momentum perpendicular to that, then you can think of this plane spinning, and the angular momentum tells you the value of that spinning, and then the torque then tells you how quickly it changes with time. So these are quantities which we now can calculate if we know the forces and the initial positions and velocities of an object. And this is what this exercise is about. So this exercise combines this new stuff and what we have seen in the first weeks when it comes to finding positions and velocity by just integrating. So here we are going to mix all the things which we have seen till now. So and if you go back to that figure, which I showed you in the beginning, this figure contains many of these links. So let's try to bring all these dots together and then look at the torque for an object which is now under the influence of an external force. So I have only one object here. What does your intuition now say about whether this angular momentum will be a constant of the motion or not? So remember now that I have external forces and internal forces. Now I have only one object. Do we then have internal forces if we think of this object as a point particle? No. So only external forces. And if I have external forces, could we then have conservation of angular momentum? We could have it, depending on the forces, but in principle, we may not have it. And this is what this exercise is about. So if somebody gives you an exercise where you have only one object, then you know, one, there are no internal forces, because we have decided in this course to think of an object as an entity, a unity. And we don't look at the molecular and atomic forces which takes place between atoms and so on inside this object. And you will see that when people do calculation for the solar system, we think of the planets as point objects. And this is clearly a gross simplification. However, it functions well if you look at the distances between the objects. And what you're also going to see is that the sun barely moves with the respect to the central mass position of the solar system. So that means that it's a good approximation to treat all the planets and the sun as objects with basically no extension. If you want to refine it and take into account all small nitty-gritty details, then you have to take into the account the extensions. But the length scales are so big in that case, the distance between the planets and the sun, that we can neglect the radius of the different planets. So the radius of the Earth is, what is it, 6,000 kilometers? And the distance to the sun is 10 to the 11th. Is it meters or kilometer? I never remember. You guys remember that. So it's just the many orders of magnitude of difference. So we can always neglect it. So this is just keep that in mind. This is one of the approximations we make in classical mechanics. So if we have one object, then we should actually expect that the torque may be different from zero, but it depends on the forces. So let's take a look at the calculations here and look at this specific system. So what we have is a initial position, initial R0, which is just given by some chosen values, and we have a Y0 times J, like this, and this is at t equals 0. And we put for convenience, we just put the initial time to 0. And then we have a force now which acts only in the x direction. So F lives only in the x direction. There is no force in the y direction. And as we've seen previously, that means that there's obviously no acceleration. So there is no change of the motion in the x direction. So we have a constant f of x, and this is multiplied by I. And we assume that this is a constant. And what we have then is that dp of x of dt is equal to times I. And this is nothing but m, and then the derivative of the velocity in the x direction, dt, multiplied with this vector I. This is the unit vector in the x direction. And then for convenience again, we choose the initial velocity, v, to be 0. And we can then integrate up. So it means that we can now find vt due to this specific force because we know the acceleration. And this is in principle equal to v0. And we put it, for convenience, we put it to 0. And we integrate from t0 to t. And then we have the acceleration, which is the same as the force divided by the mass. And then we integrate over dt. So this is nothing but what we have done before. And if I integrate this up, since I put the initial velocity to 0, this is now 0 to t. And then I have this f of x divided by m. And I have my dt, and this is multiplied with the unit vector in the x direction. And this, it shouldn't be a surprise, since f of x is a constant, this becomes simply f of x times t divided by mass times the vector I. So that's the x direction. There is no change, since there's no force in the y direction, no change in y direction. And we're assuming that we live in just 2 dimensions. So we don't have anything along the z-axis, if that's okay. So we can integrate up again. And then we find that r of t, when we integrate up, this has to be equal to an x0, which we had previously. And this x0 is just x0. So that's the initial position. And then I integrate up what I had here for the velocity in the x direction of m. So that gives me simply t squared when I integrate up. This is multiplied with I. And then I have the velocity, no, the position in the y direction, which is just y0. So there's no force here. So it remains at the same position in the y direction because there's no force acting on the y direction. So the force acts only in the x direction. Then what we are going to calculate next is actually the angular momentum. So L is simply now R times P. So we have R as a function of time. So this is R as a function of time, cross product with P as a function of time. So what I need to do now is simply to put in these expressions. So this is us setting up x0 plus, and then I have my f of x divided by m factor over half of t squared, and this is in the y direction, plus this y0 in the y direction, and this is then multiplied with the velocity in the x and y directions. But in the y direction, there is no velocity. So the only thing which I have there is actually this quantity which you see here. So this is now my velocity. I put the initial velocity to 0. And since there is obviously no force in the y direction, this means that there is nothing which happens in the y direction. So if you are at rest at time t equals 0, there is nothing acting on the y direction, nothing happens. You just stay in the same place. That sounds reasonable, right? So intuition tells us that this is what should happen. So when I then multiply this, I only need to take the cross product. And this gives us simply, if we now look at what we have here, so this is the velocity. If I multiply that with mass, this gives me simply f of x divide, and I don't divide by mass, because now I'm going to have the momentum, which is velocity times mass, and then I have times t, and then I have times the vector I. So if you go back here, the expression which I used for the velocity is this one. I multiply with mass, and then I have f of x times t here. And I just wanted to remind you of the cross product here. So you can actually write the cross product of two vectors in two different ways. So if I take a cross product of two vectors, A and B, the way you can write it, so how many of you have taken a course in linear algebra or are taking linear algebra? So you've heard about something called the determinant, right? So the determinant is a way you can use to express the cross product of two vectors. So one way you can do that is actually to set up the determinant, and that is the same. So the determinant will then be written by these three components, y of j of k, and then we have ax, ay, az, and then I have bx, the x component, the y component, and the c component. And when I write this out, this is going to be equal to ay times bc minus, and then I have az times by multiplied with the unit vector in the x direction. And then I have plus, but now things change sign here. So I would actually get bc times ax minus this is az times b of x times j, and then it has plus here, and the final one is just ax times by minus bx times ay, and multiplied with k. Now, if you look at the case which we have here, there is nothing in the z direction, no z direction, we just took it out here. So if you have a two-dimensional case, which component contributes here? This, if you go back to the definition of what we said, if you let the vector L, which is a cross product of position and momentum, that is perpendicular to position and momentum. So if we let position and momentum be in the xy plane, then clearly the only component which survives is the c component, right? So if you have a coordinate system like that, where you can place the vector in this specific way, then you don't need to calculate the two first terms. So here nothing happens in the z direction. So that means that all the components which have z here, they just disappear. So we're just left with the z direction, the vector with it multiplied with the unit vector k. So if we now look at the expression which we have here, that means that what is left then, since we only have a component for position in x and the y direction, but the force is only, or the momentum is only in the I direction, that means there is no force in the y direction. So a component like this one disappears. So what I'm left with then is an angular momentum when I do the algebra, which looks like this. L is then going to be equal to minus f of x times this constant y0 times t multiplied with k. And that means that dl of dt, which is the torque vector, is simply, when we take the time derivative, minus y times f of x times k. And unless y0 is 0, or f of x is 0, or both are 0, this quantity is different from 0. But that's something which we could have expected. So L is not conserved. Obviously, if we are just in one dimension, then this torque would be 0, because it doesn't make sense to define a torque when you're just in one dimension. So this is a typical example. If you see a problem where you have no internal forces, but only external forces, then expect that angular momentum may not be conserved. unless you have some specific equations for the forces and the positions which make that expression become equal to 0. So that was one of the ways of thinking for this next homework, which we're going to discuss more in detail on Friday. And what I thought of doing now is to introduce a very important relation. So we are going to look at conservative forces. We assume that the curl is 0 and that the force depends only on position. That means the spatial degrees of freedom. So what we are going to derive now is an important relation between a potential and the forces. So we are going to show that the force, if somebody gives you a potential energy, you can, by taking the gradient of the potential energy, then you will find the forces. And that's extremely important. There's and you're going to see this in the exercises which we're going to have. You will encounter this in the midterm. You're going to see this when we apply the gravitational force, because when you can look at a potential, when you can plot the potential, you can develop your intuition about how the system will behave by looking at the potential. So if you have a well, which looks like a harmonic oscillator, like an x squared, then you know that when the object is at the top and has no kinetic energy, it has only potential energy, and then it falls down. And then at the bottom, it has lost all its potential energy, and then it goes up again. And if there's no friction, it just goes up and down in this well. And then you can, by just plotting the potential, you can say something about how this object is going to move and what the energy is going to look like and what kind of physics you expect. So having this relation here between forces and potentials is extremely important. So the kind of things which you're going to see now, us plotting the potential and from the potential deriving the forces, is something you will do again in electromagnetism. You're going to do that in quantum mechanics. There is no difference. And you can actually develop a lot of intuition by just plotting the potentials. So that's an extremely valuable thing to do. And we are going to play around with this. But first, we need actually to show that the force can be written out as the gradient of the potential which an object moves in. Have you seen this kind of relations before? Okay, some of you have already seen that. You guys don't need me anymore. I have to give you some challenges here. Okay, let's now derive this expression, which is going to be very important and which is going to allow us to develop a lot of physics intuition. And that's what we want at the end. So we have said now that when we look at conservation of energy, so this deals with the concept of conservation of energy, and we will continue a little bit with this on Wednesday as well. So one of the things is now that we have a force which depends only on the spatial degrees of freedom. So there is no time dependence in addition to the time dependence which you have in position. And there is no velocity dependence. So as soon as you have a force with velocity dependence, energy is not going to be conserved. And we will encounter this when we are looking at friction. That will give us a force which will depend on velocity. And then we will not be able to conserve energy for an isolated system, because the system will dissipate energy to the environment. Okay, so this is one of the conditions which are important. And then the other one is that the curl of this object, curl of the force is equal to 0. And so let me write this curl down, because that's something which you guys are going to practice on Wednesday. So the curl is actually equal. So we will have the d of dy of the x component of the z component minus d dz of the y component multiplied with the unit vector in the y direction plus a d dy of, sorry, d dx, sorry. This is the partial derivative of fz minus, so this is actually z and x minus d dx f of z multiplied with the y component plus the final one, which is d dx of the fy component minus d dy derivative of the x component multiplied with k. So has everybody seen partial derivatives? You've done multivariable analysis. Good, good. And this actually leads, these two conditions, they lead to the so-called path independence. And this is what we're going to use now. Path independence, not dependence, but independence. Which means again, that when I move from two positions and the work which I perform is going to be given by an R1, I'm in a position R1 and R2, and then I can integrate the force acting on a line segment d of r. So this is now independent of path. So let us now look at the way we can define energy conservation or derive energy conservation from this, but also let's see how we can define the force as the gradient of the potential. So if we look at this expression, suppose now we have we are moving from r to a position of r plus d of r. And then we are looking at the work which is done in this, when we move this position. So this is going to be the work done from r going to r plus d of r. And this is again given by F, the force which is acting, multiplied with this small line segment, d of r. And since these are vectors, then we are using one of the things which we did in one of the first exercises. So this is a vector times a vector, so this is an inner product. So this has to be given by f of x times d of x, f of y, d of y, plus f of z times dz. Okay? Does that sound reasonable? So I'm just multiplying the two vectors. And we know that the unit vectors are orthogonal. So the only thing which survives when I multiply f with d of r are the y, x, and z components. So that's one relation which we need. Then the other relation which we're going to look at now is the usage of the work energy theorem. And we know that when we use that one, we have the kinetic energy in the initial and the final position, energy theorem. And what we know then is that the kinetic energy of m times v squared, so this is the velocity at the position r plus d of r. And I'm going to put a vector here because I'm going to keep this in two higher dimensions. We can obviously simplify to just one dimension, but then we will not get the gradient. And then we are going to have this as a potential of r plus d of r. And this is equal to an initial velocity, 1/2 of m of v0. And this is the velocity which we have at r, plus this potential at the value r. So I just use these labels, the v and v0, to indicate the velocities at these different positions. Then what I can do next now is simply to look at the difference. So if I take the difference between v of r plus d of r minus v of r, this is the same as me or us doing x plus d of x. So this is just as a component wise write out minus the potential at x, y, and z. Now, if you look at this quantity here, this is something which we now would call a dV. So a small change in the potential. I could have used a symbol delta, uppercase letter delta, but now I'm a little bit sloppy mathematically. So if some of you gets offended by my sloppy mathematics, I hope you can survive that. Right? We physicists tend to be a little bit sloppy sometimes. It doesn't mean that when we write things in textbooks that we are sloppy, but sometimes in lectures we keep a more kind of vernacular kind of mathematics. Okay, so that means if you now remember, if you have a function, suppose you have a function f, x, y, and z, you know that if you take the write out the df, this small change, you can rewrite that in terms of partial derivatives. I assume that you've seen this before. dy of f of dy plus df. So if we just use this relation here with the expression which we have, so you see now that when we now make this change, this work from r and this displacement to r plus d of r, this is actually the negative of minus dv, because normally we take the difference from r plus d of r minus the potential energy at the r. So this is the negative, and we can rewrite that in terms of the partial derivatives. So we have dv dx multiplied with dx plus dv dy, and then dy plus dv dz of dc here. So in principle, I should have used an uppercase letter delta instead of the d's. But now I'm assuming that I'm going to take the limit where dv goes to 0 and dr goes to 0. And then I can use the standard relations, which you probably have seen in textbooks of multivariable analysis. Is this something everybody's familiar with? Good, okay. Then we can go back and we can look at this expression which we had. Oops. We can look at the, let me just bring this up again. Can you hear well again? Okay. So the thing which we are going to do now is to simply link this with the expression which we have for the force. So we actually wrote this difference in terms of the force, which now is given by these different components. So that means that we are going to bring back these components, and we know that this is actually given by f of x, d of x, plus f of y, d of y, plus f of z times dz. And now we can start identifying, and you see now when we try to identify, we see that this one has to be equal to that one with a minus sign. Same with this one, equal to fy with a minus sign, and dv dc equal to fc with a minus sign. And this leads to a very important result, which simply gives us that the force is given by the derivative of the potential. And this expression which we are going to get is nothing but the gradient of the potential of dv of dy of j minus dv dc of k. And if we write this out in terms of the gradient, this is nothing but this quantity and the derivative of the potential, which now depends only on the spatial degrees of freedom. So this is a very important statement. And if you go back to that figure, this is also one of the statements which you can frame in, because we are going to use that one again and again. So often you can have an expression for the potential energy. As we will see with harmonic oscillations, we can actually derive the harmonic oscillator potential using a Taylor expansion around the minimum of a potential. And based on that one, we have a potential. And with a potential, we can calculate the forces. Or alternatively, if you have the force, you can extract a potential. So you can actually measure forces. And if you can measure the forces, and these forces depend only on position, you can actually extract an expression for the potential energy. And that's extremely valuable when you want to develop your insight about a physical problem. So when we are after spring break, when we are going to look at the two-body problems like the Earth-Sun case, we're actually going to use these things to interpret what kind of results you will get when, let's say, a comet comes into the solar system and gets deflected by the sun, or hits the sun, or hits a planet, or whatever. That will depend on the distance between the object, the potential energy, and the kinetic energy which the object has. And these are the kind of physics arguments which we can make, which hopefully develop our intuition about physics. And you're going to encounter all these things in quantum mechanics, electromagnetism, all the physics courses you're going to take. And I see that my time is over. It's always sad when the lecture is over. I have this kind of feeling. It's even sadder when the semester is over. Okay, I'm going to stop the recording here. And then we see each other Monday. Just stop the recording. Yeah, let me just stop the recording. Yeah? Oh. Just a moment. Yeah.